In this video, I will be discussing the 2018 AMC 10B question number 16. Let A1, A2, A2018 be a strictly increasing sequence of positive integers such that A1 plus A2 plus dot 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 plus A2018 equals to 2018 to the power of 2018. What is the remainder when A1 cubed plus A2 cubed plus dot 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 plus A2018 cubed is divided by 6? So you might be stumped because we are only given A1, the sum of A1 all the way to A2018. It's asking for the sum of all the cubes of these. So you might be wondering, do we have to use a sum of cubes formula? Well, no. You see, it's only asking for the remainder. And when it's asking for the remainder, you should definitely think of congruence modulo. But then, how do we apply congruence modulo here? Perhaps we could find a relationship between A1 and A1 cubed. Well, let's see. We're going to use some examples first. A1 equals to 2. A1 cubed equals to 8. A1 cubed congruent to A1 mod 6. A1 equals to 3. A1 cubed 27. A1 cubed congruent A1 mod 6. So this is pretty promising. A1 equals to 4. A1 cubed is equal to 64. A1 cubed congruent to A1 mod 6. Using this example, we can pretty good idea that A1 cubed will be congruent to A1. So A1 cubed congruent to A1 mod 6. So then we can get that A1 cubed congruent to A1 mod 6. A2 cubed congruent to A2 mod 6. A3 cubed congruent to A3 mod 6. Dot dot dot. A2018 congruent to 2018. A2018 cubed congruent to A2018 mod 6. Combine these. Find that the sum will also be congruent, which is pretty obvious. So this will mean that A1 cubed plus A2 cubed plus dot 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 plus A2018 cubed congruent to A1 plus A2 plus dot 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 plus A2018 mod 6. Okay, so now let's go back to the problem. So then we know that A1 plus A2 plus dot 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 plus A2018 will be congruent to 2018 to the power of 2018 mod 6. And now we have a huge number in front of us. So let's try to use reduction to reduce this one. And here's when you have to use an important congruence modulo identity. If you have M congruent to N mod X, then M to the Y power will be congruent to N to the Y power mod X. You can try some examples here for like if you have 6 congruent to 1 mod 5, then let Y equal to 2 to keep the number small. So 6 squared will be congruent to 1 squared mod 5. So 36 will be congruent to 1 mod 5. This is true. So using this, well, since 2018 will be congruent to 2 mod 6, So 2018 to the power 2018 will be congruent to 2 to the power 2018 mod 6. And now, we still have a huge number. But when we're asking for remainders, if you're stuck with a huge number and you can't use a reduction formula to solve this one, well, what should you do then? Try to find a pattern in the remainders then. So, pattern. You see, the perfect powers of 2 will be 2, 4, 8. I mean, it's not really a pattern here. 2, 4, 8, 16, 32, and dot dot dot. And then the remainders will be 2, 4, 2, 4. So then it's only blocks of 2. So then I'm going to divide 2018 by 2. So equal to 1009 remainder 0. Why do we do this? We want to see how many cycles of this pattern we go through. If we 1009 full cycles with remainder of 0. This remainder of 0 will link that it'll be 4. Because you see, if it was remainder of 1, it'll be 2. But it's remainder 0, so it means it's 4. Remainder of 0 means the last number in the sequence. So then you get that R equals to 4. So that is how you solve this problem. The key concept of this problem is that you need to find the relationship between A1 cubed and A1 and that they're congruent mod 6. Then you can find out that the sum will also be congruent. And then, after you can use a reduction formula here and marked in red, then you can find out that it's going to be congruent to 2 to the power 2018. Then you find some patterns for the remainders of powers of 2 mod 6. And then you will see that it will be patterns of 2 and 4. You can find out the final remainder will be 4.